Okay, what's up, everybody? We're just waiting a moment to let people join, and then we're going for it. We're jumping right into it today. Okay. Let me make sure this is at a good level of zoom, and then let's jump into it. All right, we have one person. Looks like we've waited about a minute. Get some nice colors here. Yeah, it looks pretty clean. All right. So we are on to section 2.1. This is all about contour integrals. Okay, so unlike some of the other sections we've been doing lately where I've more grabbed little theorems directly out of the book and all that, today we're going to kind of diverge a little bit from it. And I will, well, not diverge so much from the content, but diverge a little bit from its presentation, because I think that this first part is relatively straightforward, and sometimes discussing the formalism excessively right away can sort of take away from the intuitive nature of it. So let's begin. Here's the setup. We'll look at some sort of a function h from a closed interval AB into the complex plane. Let's let this guy be let's call it piecewise continuous. And if you haven't heard this term, it's exactly what you think. Composed of continuous chunks. H, you can think of it as HI from like AI, BI to C, where HI, BI is equal to HI plus 1 AI, right? Think of it just like you have like this piece, then, you know, maybe instead of having like a nice little, you know, piecewise continuous, you know, where we can kind of jump around and it's all good. We could maybe even have this suddenly break and just go like over here. We don't necessarily have to take this last little chunk. And it isn't too important to maybe I should even just technically just for a second leave this off, but here's the idea. If you had it jump like that, then everything would be bad. But you could, and I'm gonna struggle to draw this super well. You could have it like, you know, go like this, and then maybe you've got like another chunk, and this guy goes like back over here, right? And so you can have these kind of like harsh like breaks, or not breaks so much as like harsh turns. Harsh turns is the right word. That's what I was looking for. So like little different chunks, right? You know, and you're just all you have to think about is exactly the kind of picture I'm drawing. This is like a piecewise continuous. Um, and then, you know, you could just have like a regular old continuous. Um, So the idea is that you might have some like real harsh little jumps. And what I actually should say, let's even, if you're cool with it, we're gonna take it a step up, and we'll even jump to this. Let's say right now, just to set everything up all, we'll go. Let's call this piecewise C1. Um, let's say this is piecewise continuous, or we could even replace this chunk right here and say piecewise continuous differentiable. So continuously differentiable, i.e. composed of, and I'll write it as C1, one-time continuously differentiable, C1 chunks. And that's this picture. Piecewise continuous would maybe allow you to actually have like some gaps. Piecewise C1 lets you have harsh turns, and regular old continuous. This guy's also, this looks like it's C1 at least. So on, right? So we're just starting out with some various paths. We'll call these curves because they look like curves. All you have to think about with the interval is just think of like your interval AB. Just think of this like a slider drawing your curve, i.e. like if you had like a nice like a little like slider down here, and on one side was A and one side was B, and then you had like a little like button thing that you could like drag across, right? The idea is that like as you drag it across, you start to like draw your curve, right? So like if you drag it here, then you like start to pull it across, right? Then it will continue to draw your curve, right? Right? Like, you see what I'm saying? So think of the AB, that's like the slider, and then the H is the thing that draws your curve, right? So as you move the slider, this draws your curve. Okay. And so really, it doesn't have to, and keep this in mind, it doesn't have to look like, I'll probably end up drawing it like this a lot just because it is something we're used to seeing. It doesn't have to look like a regular old continuous function from calculus. That is, this guy doesn't, it can still be a function because we're taking, like, I'm not drawing this like a graph, right? It's not taking, like, it takes these guys as inputs and it doesn't like put out heights, right? It puts out points in C, which is a two-dimensional space. So really I'd have to like draw this in like R3, but that'll look weird. So just think of it as like it's like appearing in C as you move the slider. That's what's easy to think about. And so this thing as it appears in C could like go back and like cross itself and like come on down and like, you know, kind of like just zoop out like this and, kind of like do some really crazy looking stuff. It doesn't have to look like a regular old nice little line segment that's a little bit bent like in the usual like calculus context. So okay, so we got some good old fashioned curves, and what we're going to start to talk about is the idea of a contour integral. Okay. Um, okay, so let's write uh, h of t is like, oh, let's call it like u of t plus I v of t, right? We could define the integral from, say, like a to b of h of t dt to be something like, integral from a to b um, the component functions. That's like a reasonable idea, right? We could just do, okay, u of t dt plus I integral from a to b of v of t dt. Okay. So we could carry this through, and I'll say it like this: we could carry this through a function f from c to c via composition. I.e., we could do something like we could, did I do a little extra line right there? We could write like an integral from, let's write this over h, right? Of f of z dz, and we could define this as, from a to b, the integral of f of h of t. And then we could write like, you might, I wrote a t over here when I should have written a z. I'm so sorry. That's not exactly what we want to see. That's a z. The idea is that we're replacing our z and this h right here, right? We're doing a change of variables so that we'll end up over here with, I'll write it as h prime of t dt. But the whole idea right here is just that we're gonna we'll let z equal h of t, right? Then, dz dt equals h prime of t, right? And so dz equals h prime t dt, right? This little chunk is the dz, right? See, just bring this little piece over to, sorry, dt, right? See what I'm saying? Okay, so we're just doing a regular old change of variable. So we could do something like this. But how does this end up like working? And of course we could, we're taking some liberties here writing it like this. What we should maybe write is if h is actually some piecewise C1 curve with all these little different chunks, we should maybe write this as like a sum of each of these different chunks so nothing feels like too weird, because otherwise we might not actually have derivatives at some of these harsh bends right here. But we'll leave that implicit for a moment, and we can kind of, encounter that as we do some examples pretty soon. But so the idea is that and some people like to write contour integrals with like a little circle or something. And for some reason, we're going to suddenly switch from using h's to the more customary gammas that people like to use for a curve. I don't know why we want to switch from h's to gammas, but it is generally more customary to use gammas. I think h is a fine letter. It doesn't make any big difference. But let's just write gammas for the moment instead of h. We'll just make that transition now since it is more customary. So we'll write this integral. We'll write it like this. We'll define this to mean the integral about gamma of f of z dz, which we know is in fact equal to, and I'm going to write this as like a series of equalities, right? This is in fact equal to, and I'll even put the nice little summation. We'll write it like I equals 0 to, I don't know, n or something. Integral from a I to like bi, right, of f of gamma of t, gamma prime of t dt, right? This is like if we're doing it like in little chunks, and you could also replace these bi's by like ai plus 1s, right? Since where like one interval ends, the next begins, right? And okay, fair enough. This looks sort of confusing. But we can just do it like this. There's nothing too fancy there. Uh, you might ask yourself, okay, well, how do I do this chunk right here? Because f has like a real part and imaginary part. Well, we're just going to actually go through and do it. And there's nothing too fancy about it. This is proposition, I think, 2.1.2 in your book. Uh, and it might make it all seem a little bit easier because you might feel like I don't know how to handle all of these fancy little integrals in the complex plane. But just think of this: is if f is u plus iv, where these are functions u and v, right? This is the regular like real piece and the imaginary piece. I'm going to skip writing all the x's and y's because it'll just make everything messier, right? And dz is equal to like dx plus I dy, right? Think of it like that. Then f dz is something like u plus iv times dx plus I dy, right? Okay, let's just actually multiply it out. U dx plus I u dy plus I v dx minus v dy. Right? That feel fair so far? Okay. And so if we just start throwing some integrals to make this actually seem like it's slightly legit, let's sort of do an integral right here, and then okay, we can put this together and we get integral of and I'll put real and imaginary pieces, u dx minus v dy plus I, and I'll even write this integral like separately, split it up into two pieces, right? U dy plus v dx. And there you go. So you can just do this. This is nothing terrible or special or fancy. If you want to like put these in like parentheses to make yourself feel more happy about it, that's fine. But that's it. This is just regular old, like, you know, kind of path integral stuff from Calc 2 probably. Just, you know, with complex world. And so when you see like this chunk right here, you don't have to like freak yourself out. We're just gonna do everything along this type of trick right here. And so there's nothing particularly like scary about it. And once you begin to do this, there's no reason to feel particularly concerned. Now let's start thinking about what we can do with curves. So I want to begin to recover some of the more familiar pieces from calculus and use these to confirm suspicions about how things should work. The idea so far just involves us saying, okay, well, I can't really integrate, like maybe I could integrate whole things in C to C and kind of do, you know, some sort of fancy like, you know, R2 to R2, you know, vector field thing, and I don't know, do integrals like that. But you know, I could also just adopt some very easy stuff and take one-dimensional calculus and recover it basically in higher dimensional space, right? I could just go from A to B and stuff and try to do that. And this is all we're doing right now, nothing too crazy. And so as we're like using these little curves to as adapters, right? So we can take regular old kind of Calc 1 sort of things and pull them into the world of the complex. We might want to think about how these adapters work. So we could ask, how can we, I'll write it like this, get can't write for crap tonight. How can we get curves from curves? Oh, How can we get curves from curves? Nicely. Here's one way. So if you have, say, gamma goes from A on over to B, right? Okay, and we're starting at A and we're going to B, right? So we're going like, like around like this. Well, then maybe we could just go the opposite direction. We could go from B to A, right? At exactly the same speed, right? We could call this like minus gamma, the backwards version. Because if you go A to B and then you go B to A, you really didn't go anywhere, right? So, gamma, you can do minus gamma, and maybe you get like a zero path, right? Some kind of like thing where you didn't move at all. Does that make sense? Okay. And it'll end up working nicely. You'll see why we call it that. It makes sense kind of intuitively. So we could do something like that. That's kind of cool. The opposite curve, and you can actually find a very nice formula, namely like minus gamma of t will be equal to, supposing of course that gamma here goes from say like AB. I should write this as gamma of A, sorry, and gamma of B. I'm conflating the endpoints with the points that it maps to in C. I should be careful not to do that. Minus gamma would then, as we go AB to C, it would just go the backwards direction from those points, right? So it should be gamma A plus B minus T, right? So then if I plug in A, I'll get gamma of B, and when I plug in B, I'll get gamma of A, right? Oh, okay. So that's pretty easy. You can come up with this minus gamma definition pretty well, just straight up defined like that. Easy enough. You can go backwards on a curve. You could, in the exact same way I just kind of said, you could go, from A to B and then back from B to A. You can put two curves together. That is, if gamma 1, say, goes from A to B to C, and gamma 2 goes from, say, like B to C to C, and unfortunate choice of letters there, but C being the complex plane and the ladder, while C here being just another, ABC, another real number. You could form gamma 1 plus gamma 2. This kind of a curve that goes from A to B, or I should write it as A to C, right, to C. And the idea being that like gamma 1 goes from gamma 1A to gamma 1B, and then, we go from there to gamma 2C. And here I'm supposing that gamma 1B is equal to gamma 2A. Though they don't necessarily need to be the same. It just is convenient for this picture. And that's the sort of idea. If we're looking for piecewise C1 curves, obviously this kind of thing happens. If we're looking for, piecewise continuous, you can build them like this. It's a nice little trick. And notice this is when they are of the special form where the right endpoint of gamma 1, this B, happens to line up with the left endpoint of gamma 2, right? In their domain. Okay. You can sort of just put them together like that. You can imagine that there might be various ways you could put them together if you had, distinct or some differences between them, right? Maybe, gamma 1 goes from A to B, gamma 2 goes from C to D, and C is bigger than B, and then maybe like in the meantime, you just like sit and wait. I don't know. Who knows, right? There's a bunch of different ways you could do it. We'll just assume that we don't have to worry about that quite yet. Fair enough. And so you could just, keep chaining things together, do things backwards and all that. And as it turns out, everything will end up working kind of nice. So the integral about gamma of C1, and I'll even put these little like circles here. Some people don't do that. Some people do. Your book doesn't. I just want you to be clear that like when we're doing this integral with respect to gamma, it's like we're not going to write like dz's, right? We're just going to put the gamma there and it's clear that we're doing this integral with respect to a curve, and that kind of has like the, like dz's or dt's like built in, so c1f plus like c2g. Nice fact is this is c1 integral about gamma of f plus c2 integral about gamma of g. Bada boom. All right. We have that the integral about minus gamma of f is minus the integral of gamma of f. That's kind of why we call it minus gamma. Also the intuitive idea that you're just going backwards, right? Same as, switching the limits of integration back in regular old calculus. And then naturally, if you have gamma 1 plus gamma 2 f, we'll get gamma 1 f plus gamma 2, 2 f. Those are horrible gammas. I'm sorry about that. But yeah, so you can split up across curves in the kind of expected way. If you go the backwards direction, you get negative your answer, and you can you have linearity still. And so now this is proposition, I think, 2.1.3. I'm just stating it straight up because this part just is so they give all these ones without like proofs and everything in the textbook either, because it's just all coming from calculus 1 and how we defined this thing. There's no big fancy tricks. The place where we start to get to big fancy and interesting things is when we start to talk about reparameterizations. So this is a worthwhile point to bring up, and it is an interesting point, which is that you could have gamma 1, let's say, go from a to b, or from the interval a to b to c, and gamma 2, which I will draw in a different color to make everything clear, go from the exact same interval, and both of them look identical if you actually draw them out in, I have them even self-intersect all weird. These guys are exactly the same. They look exactly the same. They start and end at the same places. If you actually have them trace out, they go exactly across the same thing. But they could actually be totally different functions. That is, I could go from here to here at two totally different speeds along the exact same route. So this is kind of obvious as soon as you hear it like that, because, take your house and pick your favorite restaurant. You could drive there at a regular speed, or you could walk there and it would take longer, right? And you could take the exact same route. I mean, maybe you couldn't walk down the middle of the road. You probably shouldn't, at least. But I guess you technically could. You know what I'm saying, right? That you can go from point A to point B at different speeds along the exact same path. And so this leads to the idea of a reparameterization. And what all this is really capturing is that, like, maybe like right here, this is like gamma 1 of like a plus, like t1, and this is gamma 2 of a plus t2, and t1 doesn't equal t2, right? Think of it like, like you've gone a little bit further, but like maybe this is back here, like gamma 2 of a plus t1, right? And like this up here is gamma 1 of a plus t2, right? Like it's going at totally different speeds, right? So you can imagine going at very different speeds along the exact same path, and this is the idea of a reparameterization, and that's exactly what the definition basically turns into. So all we have to think about is that, like, we'll have gamma 1 of t be equal to gamma 2 of t up to like a relabeling of the time. So we'll call this, like, I don't know, like alpha of t for some function like alpha from AB to like AB. Here's an easy way to think of it for an example. So if you had gamma of t given by t versus like gamma of t given by t squared, if gamma is taking, we'll do 1 and 2, right? If gamma 1, and gamma 2 are both taking, say, like the closed interval from 0 to 1 into, I don't know, they can go into C. It doesn't matter. We can do t, let's do t plus like it, right? T squared plus I t squared, right? We can make it a little bit fancier if we want, do it to actually go to C. But all we have to notice is that, maybe this isn't even the perfect example because they'll end up actually following like a little bit different paths or something. But, we start from one place to go to the next place, and we just do it at different speeds. That's the only gist of it, right? Yeah, whatever. You guys get the idea. We can go different speeds. I don't need to actually like write anything out. The deal with the alpha that I'm writing up here is just that it's like a continuous function that reparameterizes time. That is if you like make your t1s equal to t2s in this, right? The thing that like assigns t1s to t2s and makes it so it's all simpatico. The nice fact about reparameterizations, as we'll deal with them, actually, here, I'll even, because I don't want, I maybe said that kind of strangely, and I don't want to send any bad messages that will confuse anybody. All right, so, I should make that slightly bigger, sorry guys. Okay, here's all I'm saying. So if you have gamma from AB to C, this is like some piecewise smooth curve. Another piecewise smooth curve, gamma tilde from A tilde, B tilde to C, right? The closed interval from A tilde to B tilde to C. This is a reparameterization of gamma. If there exists a C1 function alpha from AB to A tilde, B tilde with positive derivative satisfies alpha of A is A tilde, alpha of B is B tilde, and gamma of T is gamma tilde of alpha of T. The idea here being that the positive derivative here, what does that mean? It just means that it's increasing, right? It doesn't like have you go forward a little bit, then backwards, right? It's a strictly increasing, kind of thing going on there, right? Positive derivative. We're going from A to B. We're not going from A sort of towards B and then kind of back a little bit, then forwards a little bit, then back, and then a little bit more, right? It's just changing, like pressing fast forward or changing the speed, right? And so I should, give you precise statements here and there when necessary, but the intuition is just that we're doing the exact same curve at different speeds. And the only reason that this is worth mentioning, and the only reason that you might care, is that this can make our lives much easier. Namely, this is a fact, is if gamma tilde is a reparam of gamma, then the integral, contour integral about gamma of f is equal to the contour integral about gamma tilde of f. For any continuous f, defined on an interval, or defined on, I should say, on the image of gamma, which is, of course, the image of gamma tilde, because they're the same curve. They're just, traversed at different speeds. Okay. No fancy business there. Just, moving it about. All right. Easy, easy, easy. So this is the whole gist of it. We're just moving at different speeds, taking, going faster, going slower, and that's that. And I've been neglecting some of the statements here because it makes it feel like there's like a whole lot of things you have to keep track of, like, oh, is F defined on the right intervals? Is gamma, written as a whole bunch of different little pieces? What smoothness classes are they all? And that, of course, matters. But it really, if you dwell on it too much at first, it makes it seem like all of this is more complicated. It's not. We're just redoing Calculus 1 in a very, very basic way in the complex plane, just by using little curves as adapters to allow us to carry everything on through, and just doing it chunk by chunk. Real chunk, imaginary chunk. Easy. Okay, so there's no big scary thing there. It is nice, though, to know that our parameterization is independent of our choice of curve, or our contour integrals are independent of our choice of parameterization of a curve. And that is kind of a theme that we might begin to explore a little more. Namely, what properties of the curve are in fact themselves important? What actually matters about curves to get, this integral? So let's try something. Let's do something very basic. Let's do an example. And this also justifies evaluate. So this also justifies statements like this. Evaluate the contour integral about gamma x dz, where, of course, by x we mean real z, right? The real part of a complex number. Where gamma is the straight line from z equals 0 to z equals I plus 1. Okay, fair enough. Nothing too weird here. We're just going to go from 0 to I plus 1. All right. And if you want to go do this, the thing that I'm trying to say with the reparameterization piece is just that when we say where gamma is the straight line from here to here, it kind of belies the fact that there's actually very many different straight lines in terms of a parameterized curve, because you could travel that line at very many different speeds, right? As there's as many different lines between 0 to I plus 1 as there are functions from 0 to 1 that are increasing, right? As many reparameterizations as there are. So the fact that we're independent of reparameterization lets us avoid the technical difficulty of talking about all the various reparameterizations, and just say, gamma is the straight line from here to here, right? There's many lines, but it doesn't actually impact our answer in terms of this integral we're evaluating. Okay, so if we want to do this, all we have to do is we just go through and we actually write it out well. So this is just going to be, think of it like this. Oh, my pen is freaking out on me. Think of it like this. Gamma of t, and this is where it's real easy. What's a way to get from 0 to I plus 1? What's a really easy one? The straight line homotopy, as it's called. So we can write like 0 times t plus I plus 1 times t, right? That way when, or sorry, times 1 minus t, my bad, right? Okay, and we'll just have gamma go on the interval from 0, 1 to c, right? That way when you plug in 0, you're going to get, oh, I did this backwards, damn it. Sorry, guys. What am I, a fool? Yep, there we go. All right, how about it? Yep, I made a dumb mistake. Sorry about that, guys. 1 minus t should be over here. T should be here. Plug in 0. This part's gone. You just have this part times 1, so it's obviously that part. And then at 1, this part's gone, and you obviously just get this part, right? And so you can really do this from one point to another. For any 2 points, it's a straight line between the two. Easy. Just 1 minus t times the first point plus second point times t, right? There you go. And if you actually write this out, what is this? Well, that's all times 0, so it's, you know, just going to be t plus it, right? Oh, okay. Easy enough. And so if this guy is our gamma, then all we have to do is just go, okay, well, this is just going to be integral of gamma x dz. Well, of course, this is the integral from 0 to 1 of the real part of gamma of t times gamma prime of t dt, right? Well, what's the real part of gamma of t? Well, it's just t. So this is the integral from 0 to 1 of t times what is gamma prime of t? Well, we'll just take a derivative. We'll just get 1 plus I, right? And then we have a dt at the end right there. Okay, and so we can pull out that 1 plus I, right? And what do you know? We're just going to do some classic little bit of integrating right there. We'll get 1 plus I over 2. Bada boom. All right, so nothing too terrible. Just you have to come up with curves. Now that we've got this whole parameterization thing down, just pick parameterizations that are easy. Pick whatever parameterization is most convenient to you. And then it's just as good as any other one, as long as you, of course, satisfy the conditions of, you know, having the parameterization, having it actually be a reparameterization, right? You have to have this strictly positive derivative, and you have to have it match up nicely with the endpoints of your intervals. But other than this, it gives us a great degree of freedom. Now, there is a little bit of confusion if we talk about, you know, going from A to B, you know, or from Z1 to Z2, if Z1 equals Z2. And just a small note is that in general, if you hear, you know, like the closed loop, you know, from I plus 1 to I plus 1 or something, right? You know, like you're we'll always say that we go counterclockwise by default, like the same way you go around the unit circle. Just think of it like that, and that's just a convention. But anyways, in after this, what we'll start to get into, and I'm gonna maybe pause right here, is some facts about contour integrals and get some nice little tricks going. Little things to make our lives easier, questions about closed curves and what we get out of various closed curves here and what happens there. How does analyticity affect things? What about various paths? To what extent does the path between 2 points matter? Does it matter really at all? And it will turn out maybe that it does, maybe it doesn't. We'll find out next time. But ultimately, I want to do just like a little bit more with something like this. So here, let's pop a new layer on there. And go through a nice example or two. Okay, pull these from your book. Let's do the integral about gamma of x dz. Gamma is the unit circle's boundary, right? It's the unit circle, right? It's like along the edge of it, right? Circumference of the unit circle. Okay. So let's do gamma. We can do it in various little chunks, right? We can go piece by piece by piece. In your book, they're going to use something that's a little bit fancier. Oh, we're not going to have enough time to do this, are we? We only have 2 minutes left. Because they're going to do it in a... oh, well, here, let's actually... I'm going to save something, make our lives a little bit easier. Let's do this as... we'll call it the unit square. I.e. that's like a box around the origin, right? So we'll go from we'll do 4 curves, right? Gamma 1 of t will be t plus... oh, we'll just do t. We'll just do t. So this takes you from 0 to 1. Fair enough. Gamma 2, this will be from t between 0 and 1. Then we'll do gamma 2 of t, and we'll make this one equal to 1 plus t minus 1 I. All right, this will take you, once again, this will be from... oh, actually, we'll even do this like them. We'll do it like this. We'll go from 1 to 2, right? Then we're just going to work out... I'll just put the actual parameterization here. If you want to verify later that it's totally fine and it does indeed work, I encourage you to... that is a 3 minus a t right there. 3 minus t plus I, and this will once again, this will be for, here. Let me make our lives a little bit easier. I'm gonna... no, I'll put it all together. Whatever, that'll be fine. Alright. And then gamma 4. I was going to stack it so we could still see it while we wrote things out, but I don't know if this will be appropriate. We'll just do this as 4 minus t times I, and this is from 3 to 4. And then we'll form gamma as... and we'll take gamma from... from each of these guys. 1 plus 2 plus 3 plus 4. So we just put them together one after another, and we'll be tracing out the edges of a square, right? Easy enough, easy enough. Okay, so we compute each one in the regular good old-fashioned way. Integral of x dz about gamma 1. Well, we're just going to do exactly the same thing every time. We're going to take the real part of gamma 1, which is t, and then we will multiply it by the derivative of gamma 1 and do it dt, right? So 0 to 1 of t times the derivative of t, which is just 1, dt, and I get out 1/2. All right. Then I do integral gamma 2 of x dz. This would be the integral from, 1 to 2 now, right? Of the real part of gamma of 2 times gamma 2 prime dt. Okay, so this will be, well, what's the real part? It's just 1, and then the derivative is going to be I, right? Okay, so this will be I dt. And what do I get out of there? Well, I'm going to get I. All right, easy enough. I'm going to take the integral gamma 3 x dz. And we do the same thing again. And we're just going to get, I'm going to save ourselves some time. I'll just write out what you get because we're running actually a tiny bit over. We'll get integral from 2 to 3 of minus 3 minus t dt. And we get out of there minus 1/2. And then we do the exact same thing again with gamma 4. I should have picked something that didn't have so many dang chunks, but this goes from 3 to 4. And notice gamma 4, when we go through and we do the real part, it's 0, right? So that real part is 0, and so this is just going to be 0 dt, and so we get 0. Hence, adding it all up, 1/2 plus I plus minus 1/2, we will get out I. So 0 plus minus 1/2 plus I plus 1/2. Each little chunk. And there we go. We calculated that. Not too bad. You just have to actually go through and use the straight up definitions and do a couple of simple derivatives and some basic Calc 1. Nothing too horrific. We will do the one with the unit circle soon, and it'll be or we'll do that next time, and we'll do a whole lot more examples and a whole lot more properties, and we'll feel a little bit better about it. But right now, all you have to think about is that we're doing Calc 1 in the real part and Calc 1 in the imaginary part, and that's pretty much it. So that's all I got for you tonight. I will not see you on Friday. I will see you instead on Monday because you guys have Friday off this week. Thanks to, I actually don't know why that's in the academic calendar. Semester break, I believe. I think that might be a new thing. I don't know. But either way, it is marked as a day off, so we will take Friday off, and I'll see you next week. If you have any questions, just shoot me an email. I will respond as quick as I can. And yeah, have a great night.